Len Zen, who got a PhD under Professor Akadi. He is also professor there. And Professor Poon visited here with some colleagues. He said 15 years ago. It feels like it was 5 years ago, but it was a while ago. And he's really a leader in a couple areas, one being the use of waste materials, especially as it relates to, creating products out of concrete or cementitious materials that can be used to build the infrastructure. So he's really led the way in that area. I've followed his papers for a number of years on these topics related to recycled materials, byproduct materials, and also construction and building demolition waste that he's tried to find very useful products instead of debris to throw away. And so we're happy to have him here and happy to have him present on some of his more recent work, and just thank him for taking the time to speak to our students, speak to our faculty, and some of the visitors that are just watching in to hear what he has to say. So thank you, Professor Poon.
Okay, thank you for the introduction, Professor Rossley. And nice meeting you guys on the internet. And I'm CS Poon. I'm from the Department of Civil and Environmental Engineering. A little bit about I cannot share, I cannot move. Okay, a little bit about my university. We are in the middle part of Hong Kong. Hong Kong is a small place, 7.5 million people, perhaps. It's very crowded. We are right in the middle of the city, and we are one of the government-funded institutions. And in terms of civil engineering, we are ranked number 19 in the world in QS ranking. So we work on structural engineering, environmental engineering, material, hydraulics, geotechnical, and we have about 45 faculty members in the department and about 200 PhD students and another 200 research or postdoc and things in the department. If you are interested in joining us in whatever means, I mean, exchange students or postdoc or even a faculty member, you are most welcome to look on our website for advertisement or contact me directly. Okay, so about my research. My research is basically on turning waste to eco-construction materials, and this involves C&D waste, construction demolition waste, waste glass, ashes. Okay, although US does not use a lot of incineration technology, but in our part of the world, this is very common, and we generate a huge amount of ashes by virtue of burning waste, and then this is a major problem. And I think the US, the major ash is the fly ash, right? Coal fly ash. It is also a major problem in our part of the world. So I also work on some timber and also rubber. Okay, and but today I'm going to more concentrate on the C&D waste and the waste glass. Okay, and there was interest in the past of turning rubber into rubberized asphalt. I think this is a thing that is very, Illinois have some expertise, and we are learning. We came over at a time that we learned something from Illinois as well as from Phoenix people or Arizona State University. Okay, so about waste. Okay, C&D waste is a major item in the waste stream, and I think it's common in most part of the world, particularly in our part, because we are doing a lot of developments, demolition, and building and constructions. And this is the figures. It doesn't mean anything to you, but it stressed that it's a lot of waste. Okay, a lot of waste. And one of the waste type of particular interest is, we call this concrete slurry waste. Okay, when you produce ready-mix concrete, for some reason the concrete is returned, and so it will the aggregate is reclaimed, and then the cement in a lot of water will become waste, and we call it slurry waste. And then we have developed one way of using it in construction materials. The other is glass, and people tend to drink a lot of wine, and the glass contained beverages, and that is a major problem as well. So C&D waste come from every part of our activities, roads, okay, which is you have. And if you are using asphalt, of course it's asphalt. If the pavement is concrete, then there will be concrete waste. And then demolition, as well as construction, excavation, batching plant produces different categories of C&D waste. And when it's sorted and crushed to different sizes, it can be used for application like a subbase in road, for example, or in concrete products. Okay, but of course, C&D waste is very different from that of natural aggregate because of the containment of contaminations like timber or plastic, but also is we call the attached mortar, because in the crushed concrete, besides the natural aggregate inside, there's also the old mortar. Old mortar means the hydrated cement %. Okay, and this make the property of the what we call recycled aggregate very different from that of the natural aggregate because of this very high water absorptions. Okay, when for this recycled material, okay, when we have a scarce of resources on aggregate resources, we can use it. Okay, and particularly in our part of the world, we are lacking of landfill, and because when dump this in landfill, it is an environmental burden. Okay, and also we are running out of aggregates. So if recycling is a thing that is promoted in our part of the world, and the very basic one is turn this into blocks, okay, and without any treatment, you can crush to certain particle size, fulfilling the certain limit in a standard ASTM standard, or we in Hong Kong we use British standard, and then when you comply with the standard grading curve and test for the strength of aggregate is strong enough, then you can use for producing blocks. These are the paving block used in walkways, okay, and this is quite easy, okay. But what we try to do is to make it value added, okay, and this we have 3 generation now, 4 generation now, is we call the first generation. Try to use as much as possible recycled aggregate to substitute natural aggregate, okay. This is the most primitive type of, as I said, as long as comply with the grading, as well as some string requirement that can be used. The second generation, because we are facing also a glass problem, and with this use of recycled aggregate in the blocks, okay, so this, although it meet the string requirement, it would increase the water absorption because the recycled aggregate contain a lot of old mortar, okay, and increased water absorption meaning the blocks is easy to get dirty, okay, because it take up a lot of water, means when it's used in pavement, it take up a lot of dirt as well. So when we try to use the recycle to also use recycled glass, it is we call it hydrophobic. It does not take up too much water. It does not absorb water, and also produce some aesthetic effect. I mean, glass itself is shiny, I mean, under light. So it has strong enough for use as recycled aggregate. So we try to make the second generation block to have recycled aggregate and recycled glass together. And this contain about 8 or 70% of recycled material in it, okay? And so it lowered the water absorption, making the block more durable in a sense. Right? But there's, of course, if you are familiar with concrete, then you will be worried about the ASR, okay, ASR. But we have solved this problem by suitably adjusting the mix proportion as well as adding of certain mineral mixtures like PFA or other things. So we have addressed that, and yeah, this is the second generation. Okay, the third generation is like Professor Rosell has been talking about the photocatalyst. We put this is a third generation block. We put the photocatalyst on top of it. Okay, on top of it, in the first few millimeters, and there's different technology of blending it in. The third is intermixing, the other is coating, the other is spraying. So the photocatalyst is a nano TiO2, and with the photocatalyst, it is able to convert, okay, NO to NO3, and that would reduce certain air pollutants. Okay, and with that, okay, this is done in the lab and this is done in the factory. So we have produced the make design, we have characterized all the engineering performance of this material, and then after a lot of demonstration, and the government accept that and change the spec, and then this is commercially produced in Hong Kong. Okay, all this three generation of block. Of course, the third generation is a little bit more dear because of the use of photocatalysts. Okay, so these are used very commonly nowadays in Hong Kong. So this have the concept of recycled material as well as well-added aesthetically with the glass, as well as the photocatalytic reaction with the TiO2. Okay, so in terms of glass, why we want TiO2? I think Professor Rosell is also working on TiO2, and because of the air pollutants, right? And this is Hong Kong. It's very beautiful sometimes, but it have a nasty day. Okay, like this smog. Okay, this smog is caused by an ozone or there's part the NO partly contribute to it. And Hong Kong is very crowded, and with the vehicles, then it's quite the air pollution is quite severe. So we have the waste glass, as I said. Okay, so what the third generation of block, the concept behind the third generation of eco blocks, because there are two layers. Okay, base layer, we try to use as much as possible recycled materials. Okay, and recycled glass, recycled aggregate to provide the mechanical properties. Okay, and the strength of this is up to 60 megapascal. Okay, this is suitable for use in pavement for vehicular access, and the recycled material content is up to 50 to 60%, and this provides the strength. Okay, and recycled aggregate, of course, have to meet certain criteria, and recycled glass have the concern of ASR, but we have addressed that, as I said. If you're interested, you can go to these publications. But on the surface layer, okay, we put TiO2. The TiO2 is nanoparticle material, and this have the ability to take up to remove NO, or convert, not remove, but convert NO to NO3, and NO3 can be washed away. Okay, and in our development, we put glass on the surface layer as well. The glass, this is 5 mm, that we put particular clear glass. Okay, and the glass actually could allow the penetration of sunlight into deeper part of the surface. For example, right? Okay, when we have a TiO2, if you're only on the very top surface, then the surface area, the area that could be contacted with the air pollutant is quite limited. But because when some TiO2 is embedded in the underneath of the surface, very top surface. But when we have glass, okay, the glass allow the penetration of light, and then of course the layer of the concrete on top is is quite porous, okay? And then the air, for example, NO, can penetrate in it as well as the sunlight can penetrate in it. And there's some photocatalytic reactions there as well. So it would enhance the removal of NO, okay? So this is to show this is the surface layer without glass. This is surface layer made with sand. This is surface layer made with glass, and that is the photocatalytic removal. This is 1,000 ppb. It could reduce in the laboratory conditions, right? It's reduced to about 300 ppb. This is 70% removal for this particular sample, okay? So we are very happy with that, and then we try out, okay, and different type of glasses, color. As I said, the lighter the color, the better, because it allows better penetration. It will not absorb too much the UV or the sunlight. And then this is without TiO2, the removal is minimal, no removal. With some TiO2, there's some removal, as well as different color of glass on the top have different removal ability. So definitely the glass does affect. The white glass, that means the clear glass, okay, is the best. And in terms of, this is NO removal, right? And air pollutant, but there's also, we call algal fouling of some pavement, okay? Particularly in wet area or in humid area like Hong Kong, in the spring it's very humid. And then the pavement maybe have a layer algal bloom, algal growth, and maybe it also applied to virus or something, okay, or bacteria or something. But what we try to do is to grow the algae, okay, and then run it through this. This is a setup that we made in the lab, and then to run this algae, okay, in solution through this layer of construction materials, okay, and some of it is coated with without TiO2, with TiO2, and different type of coating methods, and then to see how much algae is growing on top of the layers, and then with the UV on, okay, and then this show the reference, okay. The reference without TiO2, there's a lot. If you can, this is, I'm sorry, it would not be great clear, but you can see there's a lot of algae grow on the surface. Algal grow on the surface, but with the TiO2 much less, and then with a different type of coating method, we have less algae grow, and this help a cell cleansing or have a method of maintaining the pavement clean in a way, okay? Because when I understand you are in the transportation group, okay, in the US or other part of the world, and you are very interested in maintaining our infrastructures, okay, clean. So maybe this is a technology may be useful, okay, for concrete or for other, for concrete itself or paving material. So with the small percentage of TiO2, and suitable condition, it could be used for making the surface clean. I don't know whether it would be useful for the current, COVID-19. We've tried with bacteria or E. coli. It works with E. coli, but I do not know whether it's COVID-19, whether it works or not. We're hoping, okay, to develop a project on that, but it's very difficult because we need a very, careful or highly sophisticated laboratory to do that, okay, for the virus. And this is the antibacterial property, E. coli, okay, E. coli, and this is in the dark, and this is without TiO2, and that is with some TiO2, a particular coating that after, say, about 2 hours, it kills all the bacteria, so under certain laboratory environment. So we published this, I think, somewhere, some time ago. So E. coli is a bacteria. The virus is not a bacteria, but it may happen something, but nobody knows. Okay, so whether it will work, and we'll wait and see. Okay, so this material is being used in Hong Kong, and this is a particular prestigious site in Hong Kong. We call it zero carbon building. It's a demonstration of green building concept. It's a model building, okay, with photovoltaics. They have biogas generator inside, and then a lot of control on energy efficiency inside. If you do come to Hong Kong, you are welcome to. You should go there, okay, for a look. And but on the foreground, and they put the eco blocks, like the third generation eco blocks there, okay. So it's quite clean. So we also develop different we call coating method with the TiO2, spray coating, deep coating, and intermix coating, and then we have developed this method with different efficiency, and then the amount of TiO2 range from very little to very high, and then the efficiency could be quite similar. So I think we are very happy with this particular method. I think we published this paper as well. If you are interested, you can go to search for it. Now, we go back to the main topic of today is CO2, right? The CO2, why we are interested in CO2 curing? Because of concrete. If you're a concrete person, you know hardened concrete, okay, is a hydrated, okay, calcium silicate hydrate and calcium hydroxide, okay. It will be carbonated. It carbonated naturally, and because CO2 is in the air, and so it will capture CO2. It will, after carbonation, it will have some pore densifications because the CH is converted to CaCO3. It leads to some densification. There's some increase in strength, increase in mass, as well as reduction in pH. And this reduction in pH is the major concern in concrete corrosion, okay, corrosion of reinforced concrete. Okay, because it's not a good thing, because concrete normally is about 12 to 13. Normally the pore solution is about 13, okay, 12.8 or something. But after the carbonation, the pore solution could be reduced to 9 and 10. So it's not good, and it leads to corrosion of the reinforced steel. But okay, but if you are talking about crush this concrete, and also using, and this concrete is used as an aggregate, okay, aggregate. Then the outside, the binder, still new binder, and then we are talking about carbonating this, the aggregate itself, okay, and this would have little bearing, we think, okay, have a little bearing on the corrosion of the reinforcement bar, okay. There are a number of factors affecting the carbonation. So the air con in this office is very, sometimes it gets to a very critical temperature. Okay, sorry about that. And there are a number of factors affecting carbonation: the pore structure, hydration product, moisture condition, CO2 concentration, and temperature. And then we are very interested in understanding how a recycled aggregate can be carbonated, because the recycled aggregate itself, as I said, has inferior property than that of a natural aggregate because of the attached cement paste or mortar, leading to high water absorption, lower bulk density, and lead to weaker interfacial transition zone. And with that, when we make recycled aggregate concrete, the recycled aggregate will lead to poor workability and also lower strength and lower durability. Okay, so this is some of the results, because it's too small for you to see. But anyway, it summarized that with the use of recycled aggregate in new concrete without any modification of the aggregate or the make design, it will lead to about 10 to 30% lower compressive strength, and also more than 30% lower in modulus, and also very poor durability as well. Okay, so, and this is the culprit, or we call it the bad thing about recycled aggregate is this is the old natural aggregate, okay? And this is a schematic of the old mortar surrounding the natural aggregate, the old natural aggregate. And this old mortar make the recycled aggregate poor. Okay, we dissolve it into acid, it is hydrochloric acid, and then before immersion and exit after, you can see before immersion is coated with the paste or the mortar. After immersion, the paste has gone because it's dissolved in the exit. You can see the exposed natural aggregate. Okay, this could be a treatment to retrieve the aggregate if we have lacking of aggregate, but this is very messy. Okay, we have a lot of waste and then making a lot of it's very high cost. So there are a number of methods of removing this mortar. Okay, there are mechanical method as well as strengthening method. Removing using grinding, ultrasonic, cleansing, heating. Heating means heat it and cool it. Okay, and then there's because of this thermal expansion and contraction, the mortar will break because of the thermal compatibility between the lateral aggregate as well as the ore mortar. Okay, but what we are trying to do is to strengthen it. Okay, strengthen it by carbonation. There are other people, including ourselves, we have done strengthening it with water glass, strengthening it with nanomaterials, and then we are particularly interested in strengthening it with carbonations. And so this is a summary. If you have interested, you can go to this publication. This is a summary of what this method do to the recycled aggregate, and then it says, okay, there's some improvement, but there are also some limitation, but it's too small for you to see. Oh, so this is the principle, okay, and then what the hydrated cement contains calcium hydrate or calcium hydroxide, particularly the calcium hydroxide. Okay, when it turns to calcite, it has some volume increase. This volume increase leading to densification, as well as the mineral change from pollutant to calcite lead to hardening as well. Okay, so this is not new. I think this is done 30, 40 years ago. Okay, by researchers in concrete. They are not doing recycled material, but what they did is to carbonate, okay, the clinker phases in cement, okay, C3S, C2, or beta C2S, they can be carbonated very quickly. The rate of carbonation is much higher than that of rate of hydration. Carbonate for, okay, a few hours would be equivalent to hydrated for a month or something, producing strength. So carbonation of the clinker phases is quite well researched, and it would produce strength, okay, because of the production of the calcite as well as the calcium silicate hydrates. Okay, and this has been considered as one of the carbon dioxide sequestration techniques, okay. Mineral carbonation promoted by IPCC, okay, International Panel on Climate Change, okay, and it did consider industrial waste, particular alkaline industrial waste like steel slag, ashes from incineration processes, cement kiln dust or concrete waste. It contains alkaline. This alkaline can be carbonated, and with this carbonation, it can be used to capture CO2 as well as produce a value-added product, okay, for other uses like recycled aggregates. So there are a lot of there are some means of carbon captures, right? There are carbon capture in brine, okay, excavations or pumped into the sea, sea storage, and also deep ground storage, but they are not leak proof. Okay, this is quite a worry. Okay, but when we carbonate it into the way, it become a very geochemical stable mineral carbonate. It would have no leakage because it's a new mineral. It's very stable. So we have CO2, okay, all around us, okay. Although the U.S. does not believe, some of the U.S., okay, people does not believe in CO2, I mean, the climate change, we do believe it in our part of the world, and then we are very much concerned with the emission of CO2 from, for example, power plant, landfills, as well as cement plant, and they produce a lot of CO2. And then if we can capture some of it, if we can remove some of it, or we can build a plant, okay, or recycle plant next to these carbon sources, we can utilize the emission of CO2 to capture our CO2 as well as to carbonate the product. So this is a schematic of what we try to do. So we have in the recycle aggregate, right? In the recycle aggregate, we have, okay, so cement basically is C3S, C2S, and other stages. When it's hydrated, it becomes CSH or CH or AFT. This is in the recycle aggregate, okay? When we carbonate it, okay, we produce calcium carbonate and other things. And then with the unhydrated phases in the recycle aggregate, there are still unhydrated C2S, for example, it still can be carbonated into these very stable mineral phases. Okay, so that is the principle behind. Okay, so this illustrates, okay, this carbonation actually it is occur naturally, but when we crush, okay, surface layer of concrete, when we demolish it, it becomes the surface area become much bigger or larger because of the exposed area after crushing. And then when we try to accelerate the carbonation through artificial, what we call accelerated CO2 carbonation process, we can produce new product and then we can capture more CO2. So what we try to do in our lab is to use accelerated carbonation processes. Okay, of course, in our lab, we try to use, first of all, 100% CO2 from a cylinder. And then we carbonate it by using different pressures and also under atmospheric pressure, like a flow through. This is the material. This is the material, and this is the, and then flow through the CO2. Okay, and this is a low pressure vessel. This is the high pressure vessels. Okay, well, so what we try to do is to artificially produce some recycled aggregates. Okay, this a lot of after a lot of laboratory works, and we produced a large batch of concrete from a batching plant, and then demolish it in a recycle plant, and then receive or collect this recycled material to the lab. And this we call a new RCA. It is 6 months old, okay, 6 months, and then there's an old RCA, which is receiving demolished concrete from real demolition site and then crush it, and then we collect those to our lab, okay? And then we try to find out what are the optimum carbonation conditions, because as we said, there's a number of factors affecting carbonations, the humidity, for example, the time, the particle size, the smaller the better, of course, and the time, the higher, the longer the better. The humidity, of course, it will be need to be in a middle range, because you need CO2, you need moisture to help the carbonation chemical reaction, as well as if it cannot be saturated to allow CO2 to diffuse in. So there are also CO2 concentration. And then we found out that, okay, certain time, okay, a few hours, maybe 1 day is enough, or even less than 1 day, okay, because the carbonation reaction go through this, okay, go through this slowing down process. And also the CO2 concentration, there's 100%, and this is about 10%, and this is 0%. And this is, we say, okay, 10% is good enough already, okay? So in real flue gas, okay, in some off gas from, for example, from power plant is about 20% CO2. And pressure-wise, there's some pressure is good, but without pressure is okay. We think that even under atmospheric pressure is okay. So after this, we provide some empirical model for predicting the carbonation, given the particle size, given the CO2 concentration, we can predict the carbonation efficiency of certain processes, and this would be helpful for using industrial processes. So these are the empirical formula that we developed, and also there's some empirical constant that are related to carbonation efficiency with different parameters like RH and CO2 concentration, for example. And this is come back to our recycled aggregate. Okay, we constant, for example, we constant the new one is 6 months old. Okay, then without carbonation, the water absorption is very high compared to, for example, this 5 to 10. Okay, for natural aggregate is about, the water absorption is about 2%. For this for the net recycled aggregate is about 7%. Okay, after carbonation, the water absorption will reduce. Okay, certain percentage, about 10%. Okay, particularly, and then if higher, this is 0.1 bar pressure, this is 5 bar pressure, and okay, there's some improvement with water absorption that is demonstrated. Okay, the 10% value is not just like the crushing value, it's a reverse of crushing value. Okay, with carbonation, there's some improvement in the strength, of the aggregate, and there's some CO2 uptake after carbonation. Okay, and then this is before carbonation. We can see there's a lot of the normal hydrated phases, calcium silicate, calcium hydroxide, AFT, the ethylene phase, calcium silicate hydrate. But after carbonation, we can see the calcium carbonate phases, like the calcite phase, alkaline is another crystal phase of the calcium carbonate, and then the pore structure has also been changed. Okay, this is natural aggregate, this is the uncarbonated, this is carbonated. So the pore is densified with the carbonation. So we try to make use of this material to make new concrete. Okay, make use, and then we just concentrate on 100%, using 100% recycled aggregate to replace natural aggregate. And with the carbonation, this is without carbonation, and then this is with carbonation, this is without carbonation. And then we see that there's some 20%, 22% increase in compressor strength when we make use of the carbonated aggregate. And also the mortars, there's about 10 to 15% improvement. This durability, this is about the cryo diffusion, there's about 35% improvement. And this is the gas permeability is about 42% improvement as well. So this is porosity. Okay, this is of new concrete, this is about 14% improvement as well. So this summary, okay, with the use of the recycled or carbonated aggregate or recycled aggregate, we can have some improvement in strength, improvement in durability, particularly. Okay, so this is particular of interest, and this is quite a highly cited material. Now you can see that. Okay, this is the natural aggregate. This is the old mortar. Okay, this is natural aggregate in the old mortar. This is the old mortar. This is old mortar, and this is the new mortar. Make it into recycle. This is recycled aggregate concrete. This is the natural aggregate in the recycled aggregate. This is the mortar, and this is the new mortar. When we try to find out the micro hardness using a micro hardness, and this is on the surface of it. Okay, on the surface of it. Okay, and then this is for the carbonated one. This is a non-carbonated one. Then we immediately can see there's some improvement of the carbonation on the old mortar. Okay, because of the carbonation. But deep down into going towards the new mortar, which is a new mortar. Okay, it's not carbonated. We can still, there's some improvement we call it inter ITC. This ITC is very interesting because when we have the old mortar without carbonation, because of the very high water absorption, there's a lot of water on top. Okay, in the vicinity of this old aggregate, and this old large amount of water making the ITC poor. And with the carbonation reaction, we think that okay, the mechanism is we think that there's a densification then of the old mortar and leading to a denser or a stronger ITC. And this improvement ITC leading to, I think we have not shown, I have not shown the result here, but it leads to a much better durability property of the new recycled aggregate. Okay, and because as we know, okay, in the concrete area, the ITC is one of the major drawback in terms of durability. But when we improve the ITC, the durability is much improved. And then we have published a few papers on the corrosion resistance, on other things. Then you can search. If you're interested, you can search. Okay. So lastly, I want to talk about this slurry waste. As I said, okay, the recycled aggregate. Producing new concrete, but return producing, okay, after reclaiming the old the aggregate, there's this waste, okay, and this way I think is everywhere, and even in the US, I think, okay, because there no matter what, you have some wastage, okay, and then we've analyzed this waste. This is similar to not similar to cement. A lot of because CSW contain a lot of silicate dioxide, because it contains a lot of contains PFA, it contains silica film higher than that of cement. Okay, the silica dioxide, aluminum oxide higher than that of cement as well. But it can be carbonated. This concrete slurry waste can be carbonated actually, and then when we carbonate it, it takes up about 15%. Or okay, 10% of cement. This concrete slurry waste, when we carbonate, it takes up 10% of cement, 10% of CO2 in terms of cement mass. Okay, and this shows the change of pH value after carbonation. Okay, and then change of the microstructures. But what we try to do is to make it to a truly eco-friendly material with the fresh waste, with the waste. Okay, this waste, although is cement with a lot of water and also some very fine sand. Okay, and after 2 to 3 days, it's still workable. Although it's a lump, after 2 days when we mix it, it's because it's very high high water content, it's still workable. When you mix it with recycled material like recycled aggregate, fine, to produce a block. Okay, and then carbonate it, and then carbonate. Okay, we can produce manage to produce string after a few hours of a string is already good enough for shipment. Okay, rather than you have to wait for a few days. Okay, and this material, so we are using in this particular mix, we are using the recycled concrete slurry waste as the binder, and we are using recycled aggregate fine as the aggregate, and then try to produce a material by carbonate it, and then the carbonation reaction would produce a very fast carbonation, producing string, and within 6 hours it can be delivered, and this could also take up about 5% of CO2. Okay, this is the CO2 uptake by the concrete slurry waste itself, but after mixing with the recycled aggregate also take up CO2, but after mixing it, the CO2 uptake is less, but still it take up 5% CO2. I think I skipped that. So not only it have good strength, it use waste material, but it can also reduce the shrinkage, because shrinkage is caused by CSH, right? The dehydration of CSH, but there's all the CSH there is converted to some sort of carbonate, and then the shrinkage, not all, okay, some of the CSH, and then their shrinkage is much reduced. And then we done life cycle analysis of it, and then conventional block, okay, this is made to a block, okay, or partition block. We can make use of it to, and then there's conventional, we have this carbon footprint and energy consumption, and then with this material and production process, we can reduce about 90% of carbon footprint and also 50% of energy. So I hope this works. You have some? Yeah. It takes about 30
In
seconds.
our atmosphere, the concentration of CO2 due to human activity has significantly increased in the past 50 years, which is the most important cause of global warming. In Hong Kong, an ambitious target has been set to reduce more than 50% greenhouse gas emission by 2020 at the 2005 level. The Hong Kong construction industry, as the second largest economic sector, is proactively looking for improvement opportunities at the frontier of sustainable development. By curing mixtures of both fresh and old concrete waste with a waste CO2 source, a new technology has been developed to produce carbon-neutral concrete products. In concrete batching plants, aggregate and water reclaimers are normally used to recycle coarse aggregates, sand, water, and cement slurry waste from production wastes. After all, the cement slurry waste is disposed to landfill as there is no other effective way of reusing it. A research team therefore consisted of academics and engineers have been established to explore ways of reusing the cement slurry waste. More than 5 years' efforts devoted by the team has eventually brought to the birth of carbon-neutral concrete products. For instances, dry partition wall blocks, which not only are made from waste, but also cured by waste CO2. In the Polyu lab, the fresh cement slurry waste from concrete plants is firstly processed to a calcium and silicate-rich slurry paste. Then, the paste is mixed with fine aggregates produced by recycled fresh or old concrete in proportions determined upon required concrete performance. The mixture can be further fabricated into better quality dry wall blocks at optimized CO2 concentrations for a few hours identified by the research team. The fresh cement slurry previously dumped to landfills is now turned into a concrete product that captures CO2 at a rate of more than 0.11 kilogram per kilogram from CO2 emission sources such as cement plant, power plant, and landfill sites. This innovation does not only completely eliminate waste associated with concrete production, but also brings truly neutral carbon footprint concrete products to the construction industry. Pilot industrial applications of our innovation are on the way. When fully utilized, savings of 160,000 tons inert waste, 8,000 tons greenhouse gas emission, 80,000 cubic meter disposal at landfill, and 20 million Hong Kong dollars waste management cost per annum can be expected.
Okay. So with that, I think I finish. And if there's any questions, you are most welcome to ask, and then we can have some exchanges. Thank you.
Thank you, Professor.
Yeah.
We have time for questions in the chat, or you can verbally raise your hand.
So we have Professor Nishat Garg. You can go ahead.
Hey, Professor Poon. Thank you so much for this very stimulating talk. I had a question about the incineration ashes you mentioned in one of your slides. I wanted to ask you, how has been your experience working with those ashes, and what potential pathways do you see for their beneficial utilization in the future?
Oh, yes. We have a very active program in our university. Under my group, we have a few PhD working on different types of ashes. And for incineration, okay, processes, there are the municipal solid waste incinerator, and there's also the sewage sludge incinerator. For the MSW incinerator, we are particularly interested in working with the bottom ash. Bottom ash is a potential to be used as a construction materials, and actually we publish a number of papers, okay? And there's a great need, okay, in our part of the world, because in China, there's more than 500 okay, incinerator plant, okay, and all the ashes are waiting to be disposed of or reused. And so we are trying to develop new techniques or value-added techniques. But for the fly ash, it's difficult because it contains a lot of heavy metals as well, chloride, as well as some dioxins. Okay, and it's classifiable as hazardous material. But their technology trying to we call it virtuify it. Virtuify means using very high temperature to melt it into ceramic. And after melting to a ceramic, it can be used as an aggregate. So there are active research, I think, in quite a number of parts of the world doing that. And then we hope our process, okay, turn it into, we have just finished yesterday in a plant trial, actually in Hong Kong, to try to make the bottom ash into a value-added lightweight aggregate. And then we hope the plant trial is successful, and then we can convince the government. There is a government-funded project actually to try to utilize it. Yeah, it's very active research going on, but I don't think there's very much real application as yet because the specification still there's some way to go because convincing of the regulators from waste to resources is always difficult. Okay, thank you.
So right now, is it mostly being landfill? Like, what is the current
state? Mostly landfill. Yeah.
Thank you so much. Yeah, we are starting to just look into this, so it's a very, very interesting topic for us as well.
Thank you.
I'll look up your papers on this.
Thank you.
Thank you.
Hi, this is Angel Mateos from the University of California Paving Research Center. Well, Professor Poon, thank you very much for the presentation. My question is, do you know of any location in the United States where this procedure for introducing the carbon dioxide into the recycled concrete aggregate has been implemented
in the United States?
Yes.
I think there's a technology marketing in the North America, I think, doing CO2 curing of concrete, okay? That means when they produce new concrete, they cure it and then densify the surface of new concrete. I think Professor Rosner may be aware of that group, okay? There's some researcher in McGill University, okay? Professor Shao or something is doing that.
Yeah, I was wondering.
Not the recycled material though. I'm not aware of recycled material, but for new concrete, some.
Is any full-scale application to recycle concrete aggregates? Other than laboratory experiences, if there is any full application here in the US?
Sorry, I don't.
I think the question. The question was: is there applications of recycled aggregates in the U.S.?
I think there's very few. In the U.S., the problem U.S. is too big. It's very big, and then you don't need recycling. As somebody said, because you can dump everything in landfill. There's so many landfill, and then the cost-wise, I mean, recycling cost-wise is compared to landfilling is more costly, yeah. And then you have so much resources in terms of natural aggregate, and so the driving force for recycling still is not very high. Okay, very strong in the U.S., but in our part of the world, it's very strong. In Europe, it's very strong. That is the difference between the U.S. and the other part of the world. Yeah.
Yeah, I'd like to add that we do use recycled concrete that we usually use as a subbase. I mean, that's the cheapest way.
Yeah. That's without any treatment or something.
Yeah, that's the most common.
Yeah,
it's easy.
Right. Yeah, the main reason why I was asking that question is because I was wondering about the cost of implementing that technology in the real production of concrete in the field. Like if that, I am assuming that the cost of introducing the carbon dioxide in the recycled aggregates is going to be very high. So that's why I was asking about.
Yeah. If you try to industrialize it, I think you need to have a carbon tax. For example, if you capture CO2, right, then it will give you some financial advantage. Also, because in the UK, for example, there are aggregate tax, carbon tax, everything is taxed when you are polluting the environment. Of course, there are industrialists who want to make use of this to avoid these taxes, right? Or to earn funds, earn some money from this policy, and then they would do it. But if there are no tax or no government intervention, of course they would not do it. In terms of pure economic, it's not feasible. Okay, without government regulations.
Yeah. Thank you.
Thank you.
I think Richa, you have your hand up.
Yes, thanks for the presentation, Professor Poon. I have two questions. Like, first is how long the photocatalyst on EcoBlock is able to remove the pollutants at an efficient rate? And other question is like, what strategies would you suggest to prolong the life of coatings on pavements or these kind of blocks?
Oh, the life of photocatalysts, right? Yes, it's a very good question. Nobody knows actually. We try to evaluate the long-term durability of this material by doing accelerated tests in our lab, okay, and then putting it to very severe cycle operation and weathering and things. We think that, okay, with normal type weathering, okay, abrasion and dirt, okay, dirt accumulation of, if you have proper maintenance of the surface, like washing, like, okay, using a water gun or washing, okay, that is good enough. And then I think we can recover, okay, certain percentage, like 70%, okay, of the original photocatalytic properties, because we have demonstrated photocatalyst is a catalyst. It will not be involved in the chemical reaction of the cement. It's the TiO2 stay as TiO2, okay, as it is, okay, without involving in the hydration reaction. But we also did some experiment when you have oil spill, okay, organic substances on the pavement, then is a problem. When is the catalyst is covered by organics, it will not be washed away, or it will not be recovered because the oil, okay, is very, in a way, durable. When it covers the surface of the TiO2, it will not work. And so it depends on how the surface is maintained. Okay, and so if you want to really use it, and then the pavement okay, engineer or the authority need to have devised a strategy like washing, periodic washing, as well as grinding, for example, okay, polishing the surface, not polishing, only grinding. If the surface is obsolete, because we are talking about a few mm thick, okay, the surface of which contain the photocatalyst. If we can remove the already, okay, worn off surface, it could be exposed again. So maybe, okay, but it's not being practiced yet, I'm afraid. Okay, we have put that into surface, and then and we are still monitoring the result. I think after a few years, it's okay, still okay. Yeah.
Are you using this as a coating or an introduction of the cement? Because you're carbonating as well.
Sorry?
Did you carbonate the block?
No. This is not carbonate. This is just TiO2. This two technology. Yeah.
Gotcha.
Yeah, okay.
Did you ever try it carbonated with the block?
No, it's the carbonate of the aggregates doesn't matter. Carbonate the aggregate and then put the aggregate into the block is okay, as long as you are not carbonating the new cement. If you carbonate the new cement, the surface is very dense, and then the TiO2 will not be exposed, cannot be exposed to the air or something. Yeah.
Okay.
Richard, did you want to circle back to your first question, or the answer?
I think like I got the answer.
Okay. So we're running out of time now. So if there's another question, that's the time to do it. So Aniruddha, you'll be your last question.
Yeah, I mean, if you do have questions, you're most welcome to email me. or using my website to see some of my research there. But website is quite old. You can go to my university website. You can see some of more newer informations. And we do have for last year, I do wish to come to Champagne. Champagne is a very nice place. So Euro, right? So different from Hong Kong. It's everywhere is country and very nice. The drive from Chicago to Champagne is really beautiful. I wish I could come some days in the near future. And you are most welcome to visit us also in Hong Kong. And we do organize conferences, and in Hong Kong is an international city. And so you are most welcome to visit us.
Thank you.
Thank you, Professor.
Maybe we'll have one last question from Aniruddha.
Hi, Professor. Thank you for the presentation. I have a quick question about coating versus using TiO2 in bulk. So right now, what's your view on that? Like, do you think using coating is much more cost effective, or do you think using TiO2 as a bulk addition has a chance?
This is controversial, okay? If it coating, I mean, the durability would not, I think if the coating, of course, when the material is not subject to abrasion or subject to contact, because when you have contact with shoes, with people or vehicles, it will deteriorate very fast, okay? But it's a coating. But when we have when the TiO2 is sit in the pores, okay, it will survive. Some of it will survive the abrasion. That's what we do, okay? After 500 cycle vibration or abrasion is still okay. Okay, the percentage of removal still can maintain at 80%. That's why, okay, so it's subject to the application. If you are not, the material is like on a wall, okay, nobody touch it, and coating is good, okay? But when it's on a surface, on a roll, maybe is not so effective for coating. Yeah.
Well, I appreciate your presentation.
Thank you.
And your answering your questions, and you're definitely welcome Champagne anytime.
Thank you for the students, huh? Isaac and also Jeffrey. Jeffrey, is your student or what? Jeffrey?
Yes, I'm a student of Professor
Thank you for trying out I was in a mess yesterday when try out but today is okay. Everything works out very good. Okay.
All right. So to wrap up, I just want to remind everyone that we still have one more session next week. It's also from someone in Asia, I believe China. So it's going to be at the same time. So it's next week, Thursday at this time. So I hope you guys join us too.
Okay, bye-bye.
Yeah. Professor Poon, thank you so much. Just want to tell you, this is a student-run activities, and we really appreciate you being with us. So.
Okay. Thank you. Thank you.
Yeah.
Nice seeing you. Nice seeing you on the internet. Thank you. Bye-bye.
Thank you.
Bye.
Bye.
So thank you, everyone, and see you next week. Goodbye.